For decades, automotive safety relied on a straightforward assumption. If a car's hardware and software operated exactly as designed, the vehicle was inherently safe. But the real world is messy. A car operating with flawless electronics can still encounter a severe snowstorm, a sun glare that blinds its cameras, or a pedestrian suddenly darting into the street. This vulnerability drove the creation of ISO 21448, known in the industry as SOTIF, the safety of the intended functionality. Engineers must now design behavioral intelligence that maintains safety even when every hardware component and software line works perfectly. An impeccably built engine offers zero protection if the system itself doesn't know how to navigate the unpredictability of an open environment. To build this logic, engineers start with the vehicle-level SOTIF strategy, or VLSS. Think of this as the macro-level rulebook that establishes the absolute boundaries for what the vehicle is permitted to do. Those broad rules are then handed down to the driving policy, which acts as the micro-level, real-time executor on the ground. This policy lives precisely inside the classic sense, plan, act engineering loop. It operates as a strict gatekeeper, taking the raw, imperfect data gathered by the sensors and deciding exactly what physical commands should be sent to the brakes and steering. By sitting directly in the middle of this loop, the driving policy constantly translates abstract safety principles into split-second physical survival decisions. During normal driving, the driving policy projects a safety envelope around the car. This mathematical boundary expands for higher speeds or slick roads. If an external threat violently breaches this space, the system executes a proper response, computing aggressive deceleration or an emergency swerve. It makes these choices under strict programming constraints. The maneuver must prioritize accident avoidance without violating traffic laws, and the logic is specifically designed not to penalize the system for reacting to a threat initiated by another driver. The algorithm isn't trying to read minds or predict the unpredictable. It is rapidly calculating a physically defensible reaction to sudden chaos. But even the most sophisticated avoidance algorithms have limits. Every driving policy is tethered to an operational design domain, the specific geographic and environmental limits where the system is guaranteed to function safely. Imagine a vehicle driving into a sudden blinding whiteout. The LiDAR lenses become packed with snow, and the camera sensors are rendered entirely useless. The car is forcibly ejected from its safe operating domain. In this severely degraded state, the system recognizes that attempting to push forward and complete the trip is the greatest possible hazard. The overarching safety strategy immediately activates the minimal risk condition. The driving policy suppresses its original destination, triggers emergency protocols, and carefully maneuvers the vehicle to a complete, safe stop. Executing a graceful surrender into a minimal risk condition is a requirement of machine intelligence. When the environment becomes unmanageable, the system prioritizes a safe, stationary state over the risk of continuing blindly. This presents a massive engineering challenge. How do you mathematically prove that this behavioral logic is safer than a human before you ever deploy it on public roads? The validation process begins with leading measures. Developers run millions of predictive simulations, subjecting software to severe envelope violations and calculated near misses. This extreme virtual testing uncovers hidden vulnerabilities, refining the system's reaction logic without risking a single piece of physical metal. That data is then paired with lagging measures. This is the empirical validation phase, tracking actual crash statistics, accident severity, and component failures from physical fleet vehicles driving millions of miles on real asphalt. An autonomous system is only declared ready for the public when its simulated predictions perfectly align with a mathematically acceptable rate of real-world physical outcomes. The ISO 21448 standard was not written to guarantee a physically impossible utopian world completely free of accidents. Its objective is to ensure that the autonomous vehicle will never mathematically execute a command that initiates a hazard of its own making. It mandates the creation of an exceptionally defensive driver, projecting an algorithmic shield against the daily friction of the open road. These standards turn autonomous vehicles